Hello, good afternoon. I see people are connecting. We're going to start our Astroparticle and Cosmology session 1 today. We have 3 very interesting talks. The first one on theory overview, the second on experimental overview, and the third on something which is very hot today in astroparticle and cosmology. And the first speaker is Timothy Linden, whom I asked to share the screen and start this talk. You have got 30 minutes, Tim, with 5 minutes for questions.
Great.
Thanks.
Thank you so much for having me. Today I'm going to talk about the current prospects and future of indirect dark matter detection and searches for thermal WIMPs. Everything we know about dark matter stems from its gravitational interactions. Observations like the cosmic microwave background, the formation of large-scale structure, or the collision of galaxy clusters tell us a lot about and give us extremely detailed models about where dark matter is and how it gravitationally interacts in our universe. Unfortunately, it gives us almost no information about dark matter's particle properties or any non-gravitational interactions. For example, it only constrains the mass of the dark matter particle to within about 87 orders of magnitude. So within that, there's a huge sea of possible dark matter models, going from things like axions, primordial black holes, stereo-neutrinos, or possibly weakly interacting massive particles, which is what I will mostly talk about today. So why do I focus on that model? And why do I want to rule out that class of models in one go with indirect detection experiments? The reason is that the dark matter density in WIMP models is well motivated, or in any thermal relic dark matter model, and I will use those interchangeably. Dark matter interacts with baryons in the very early universe through thermal interactions and achieves an equilibrium density, which then freezes out over time as the universe cools and expands. The WIMP miracle is simply the fact that if the expansion happens and dark matter continues to annihilate residually at a strength that is given by the weak nuclear force, which of course we know about, then the relic density that you get of dark matter today is about the observed number. The second part of the WIMP miracle is actually the WIMP annoyance. It's the fact that this is almost a mass-independent statement over many, many orders of magnitude. Dark matter particles ranging from about 10 MeV up to 100 TeV can achieve the same relic density today from weak interactions. But most importantly, for the point of this talk, this gives us a target, the canonical thermal WIMP annihilation cross-section, which has a value 2.2 or so times 10 to the minus 26 centimeters cubed per second. And that is the residual rate at which WIMPs should continue to annihilate today, potentially producing emission that we can see. But our gravitational understanding of dark matter actually gives us much more information about than just this. It tells us where dark matter is expected to be found. Where is the dark matter density high? It's consistent with the centers of galaxies. What does the dark matter density profile look like? It peaks towards the center of these galaxies, which with profiles that go from 1 over r, maybe are chord near the center, maybe rise even steeper near the center of galaxies. So we know the types of locations that we want to search for dark matter. It also tells us the energy range we want to search for. If this is the annihilation of particles that have energies between a few MeV up to 100 TeV or so, then the annihilation products will fall at energies that are a factor of 10 or so below that. So we can look in gamma ray astrophysics or in relativistic cosmic ray astrophysics for evidence of these particles. And these are the two regimes I want to talk about in this talk. A dark matter particle annihilates somewhere in our galaxy, not to scale, and we want to record it here somewhere at Earth. It can directly produce gamma ray emission. This is a powerful probe because we know we have morphological information about that gamma ray. We know where it annihilated because we received the signal directly at Earth. It can also produce charged cosmic rays, and those bounce around through the galactic magnetic field, so we lose that morphological information. But on the other hand, because dark matter is its own antiparticle, or because dark matter and anti-dark matter annihilate to produce equal amounts of matter and antimatter, we can search for the antimatter signals specifically, which is a powerful probe because our universe is made mostly of matter. Perhaps the most important takeaway of this talk is that we can already be seeing these events. So for example, let's look with the Fermi Gamma Ray Telescope at the center of our galaxy. Let's put in that thermal WIMP annihilation cross-section, which we already know about in our thermal WIMP model. And let's take a normal dark matter density towards the center of our galaxy. How many photons from dark matter annihilation should I have observed in my instrument? And the line that gives us one observed photon falls far, far below the thermal annihilation cross-section. Or similarly, dark matter models that annihilate at the thermal cross-section should give us, 10 to the 6 events at low dark matter masses, up to a few events for even the highest dark matter masses. For any thermal WIMP annihilation model, the Fermi-Lat telescope has seen a gamma ray which was produced by a dark matter annihilation event. The same is true for antiprotons. Now take the AMS-02 instrument aboard the International Space Station and ask the annihilation cross-section that would produce one antiproton observed by that instrument. And it again falls many orders of magnitude below the thermal WIMP cross-section. And this is to me why this field is so exciting. We're not looking for one event against a background of 0.001 events. We're looking for thousands of events against a background of tens of thousands or hundreds of thousands of events, where we need to understand the systematics of our astrophysical background subtraction to make headway. And this is a tractable problem. Of course, this is not easy. So here's our dark matter model, the number of gamma rays within 10 degrees of the galactic center, a very nice dark matter prediction, very detectable, thousands of gamma rays from this signal. And if we actually look with the Fermi-Lat and take data, this is what we get from totally different observations. The astrophysical flux depends on the star formation rate in the Milky Way. It depends on the diffusion of cosmic rays through the dense galactic center region, and maybe the activity of Sagittarius A star. And it produces emission that's about a factor of 10 brighter than our dark matter prediction. The story is the same for antiprotons. This is a totally different dark matter signal. Now it's mostly the local dark matter annihilation rate, but it produces a very observable signal. Again, thousands of antiprotons. The astrophysics produces something that is, again, 10 times brighter. And this is extremely frustrating, right? And from some sense, as a theorist, you either want the dark matter signal to be dominant, in which case you can look for it, easily rule it out, or find it, or you want it to be 10 orders of magnitude below your astrophysical signal, so you know not to waste your time looking. In fact, it's a factor of 10 below, just hard enough that we need to expend the effort to try to find this. On the other hand, maybe we've just met the enemy, and the enemy is us, all these baryons in astrophysics that we need to subtract in order to get the dark matter signal. So I want to look in this talk at the antiproton excess. And the reason I want to do this is that it's a model for all of the things that go into these sorts of studies from every single direction. I also think that this is a particularly exciting potential excess now, and there's still future work to be done. But mostly I want to think about this as a template for all of the different dark matter searches that you can do in astrophysical regimes. We measure the antiproton excess as follows. We look for the flux of antiprotons observed by, in this case, the AMS-02 telescope, divided by the flux of protons. And the reason we do this is to cancel out certain detector systematics that might be common to any cosmic ray event, whether it's a proton or an antiproton. Most protons come from astrophysics because stars explode and accelerate lots and lots of protons. The dark matter signal looks like this. It's a bump. It's about a factor of 10 below the mass of the dark matter particle, shown here for the best fit value of 74, which you wouldn't know yet. But here's the dark matter produced flux. The astrophysical model looks relatively smooth, something like this, with an antiproton ratio of about 10 to the minus 4. Early observations were not that exciting. The Caprice instrument, found antiprotons for the first time and measured a flux and a ratio. And these observations continued to look a lot like the astrophysical model. As data from BESS, heat, more data from BESS, the Penmella telescope finally gave us a lot of energy resolution and a lot of statistical sensitivity to these things. And there start to be some interesting little features here, and maybe we can start to probe them. Then the AMSO2 instrument released its first data, and you could see the change over the last 20 years. These error bars are ridiculously small. They're invisible on this plot. And they're so tiny that you can find excesses in this data. One of them you can spot by eye. It's right there. This we think is due to astrophysics and the production of antiprotons within the sources themselves. And then there's a second excess, which you can't see by eye, but which is potentially statistically significant based on the very small statistical uncertainties in this data. In fact, it was pointed out in 2016, 2017, that there was an excess in this data that could be fit by a dark matter annihilation model. So here by Sui et al. Is the AMSO2 data. Here's an astrophysical background model in blue. You can see it's falling just below the data here at about 5 GeV. And here is a best fit dark matter model that improves the fit to this data by 5 sigma. In the paper by Cuoco et al., they both came out on the same day. You can see the excess here in the residual plot. There's a little bump here in the background only model that can be fit by a dark matter model. So this is extremely exciting, but it's a very, very small signal. Even so, it ends up that it is consistent with the dark matter model, where the dark matter is annihilating exactly the thermal annihilation cross-section. Not producing one event that we can see, but producing thousands of events that potentially contribute to this data at the few percent level. Unfortunately, when you have such statistical precision, you have to get everything right. And when you have a 1% excess, you have to do many, many things correctly. That involves the production of antiprotons in particle collisions. A proton hits gas in our galaxy, it produces jets, those include antiprotons, and we need to get that particle physics modeling right. We need to get the propagation of those protons and antiprotons to Earth correct. We need to worry about solar modulation, which is that before the antiprotons get to the instrument itself, they have to fight through the last few hundred AUs into the Earth, past to the solar wind. And the solar wind can exert an important influence on charged cosmic rays getting closer and closer to the Earth, especially at the few percent level that we now care about. And then you have to worry about instrumental effects. We have an observatory in space. We're measuring lots and lots of different cosmic rays through it, but might there be some, uncertainty in the energy reconstruction or something like that produces a bump. So these are all the things you can worry about, and all the things you have to worry about when you're worried about things that are, signal to noise of a few percent. So let's go through them in a little bit of detail and show that they're all really uncertainties that matter now. And that's why this field is both difficult and exciting. So here is the antiproton flux again from AMSO2. This is the uncertainty on proton-proton interactions producing antiprotons plus other junk in astrophysical environments. And it turns out that this has uncertainties that are at the order of 5 to 10%, which is not something that starting this field I would have expected, that the particle physics uncertainties were such that it might actually swamp an astrophysical signal that I always think of as much more uncertain. But there are different reconstructions of the proton-to-proton cross-section, and this is lying a little bit. A lot of the uncertainty comes from scenarios where the charged cosmic ray is actually a helium nuclei, and it's hitting a proton in space, or vice versa, you're hitting helium nuclei in space. And that adds to the uncertainties in this cross-section. But of course, they're measurable, and our statistical precision will improve. You have to worry about the propagation of those antiprotons to Earth. And the way we do that is measure lots and lots of nuclear rates, cosmic ray rates, in the AMSO2 experiment for different charged cosmic ray species, which we know aren't produced by dark matter. So things like cosmic ray helium, which is accelerated in supernovae, along with carbon and oxygen. And also what we call cosmic ray secondaries, lithium, beryllium, and boron, which are not accelerated directly in supernovae, but are instead produced when cosmic rays like carbon and oxygen hit gas in our galaxy and spallate to produce lighter cosmic ray nuclei and protons and things like that. And you can see that these have different spectrums, and they're well measured with extreme statistical precision. And so we can use these primary and secondary cosmic rays and their interplay to basically chart out the propagation of cosmic rays through our galaxy. More and more, now that we worry about 1% statistical precision, and we used to only worry about things, at 10% levels or, factor of 2 levels, well, in the past, we used to be able to deal with these models where the galaxy was just a slab. Cosmic rays worked everywhere, the same way, everywhere in the galaxy. They diffused, the galaxy was like a cylindrical block, and you just let the cosmic rays bounce around in the magnetic fields, which were constant over the whole galaxy until they made it to Earth. As we worry about things at the few percent level, we have to get the statistical precision to do these things, and we have to worry about the inhomogeneities of how cosmic rays diffuse near and far away from sources themselves. We have to worry about that solar modulation. But because we now have so much data, we can actually chart out the time-dependent flux of protons hitting our instrument. Galaxies don't change on day-to-day timescales, but the sun does. And we can use that time variable information to remove this uncertainty from our models. We're now building very detailed models of the flux of cosmic ray protons on a month-to-month basis, matching AMSO2 data. And finally, we have to worry about instrumental uncertainties. And here are the number of antiprotons, along with the statistical uncertainties in red, and the instrumental uncertainties from the AMSO2 in blue, which are often much larger. And at present, we don't have a good covariance matrix for the energy dependence of these, the correlation between the energy independence of these uncertainties. So if there's a bump in one bin, we don't know how that correlates to the probability of there being bumps in nearby bins. And that's something we have to better measure. So you can see there's a world of uncertainties, and getting a 1% measurement is difficult. So now that you're all appropriately inspired, let's first examine the possibility to fight through these obstacles directly, dealing with all these different uncertainties. And as someone who focuses on the astrophysics, I want to think about the astrophysics uncertainty in particular here. How do we deal with inhomogeneous diffusion of cosmic rays? And there's been some really exciting developments in this field over the last few years. We have generally thought, and it's true, that the total cosmic ray density is dominated by protons and other hadrons. We see that from the sources themselves. Here's a flux of cosmic ray protons and heliums from simulations of protons and electrons from simulations of supernovae. Here are the proton and electron fluxes that are reaching the Earth and are recorded by AMS. And you can see protons dominate by a factor of 100 or so. But recently, we've seen some observations that challenge this. These are new sources observed first by Hess and Hawk, and first noted by the Hawk Observatory, which is shown here, of extended leptonic TeV gamma ray emission, extending to energies of tens or even hundreds of TeV that are surrounding the position of known middle-aged pulsars that are far from their original supernova remnant. So here's Gaminga, and this is what's commonly known as the monogen pulsar here. And you can see the full moon to scale. These things are huge on the sky. This tells us something, because these things are dominated by the electrons and not the protons. Most of the emission, the TeV gamma ray emission, is being powered by what we thought was this subdominant electron component. And there are two fundamental reasons for that. The first is just that electrons cool quickly. Most of the protons probably escape the region around the pulsar or the supernova remnant. They leak out into interstellar space, so they don't produce these bright blobs of concentrated gamma ray emission that we can see. And we knew that, and that's been known for a long time, that inverse Compton scattering is very efficient at cooling particles. But what appears to be new is that the cosmic ray electrons, as they're escaping and cooling rapidly, can produce a sharp gradient of charged particles. And that gradient of charged particles can, through a process known as cosmic ray self-confinement, produce magnetic field turbulence that actually freezes the cosmic rays in place temporarily, causing the electrons to stay in positions near the pulsar for longer periods of time and cool more, producing brighter, more intense emission. And what's so interesting is that gives us the indication that cosmic ray diffusion is very inhomogeneous throughout the galaxy, and telling us where those inhomogeneities are. We have to look only at this map of the diffuse sky, or the galactic plane, and look for where there are bright spots, and that tells us where cosmic ray diffusion is confined. So here are models of the diffusion constant falling from the default galactic background by several orders of magnitude for a few 100,000 years after the pulsar is produced, and then slowly returning back to the default value. And here is what a population of thousands of pulsars throughout our galaxy might look like, creating regions with very inhibited diffusion throughout the spiral arms. Now, there are still many models at play here. It's possible that these electrons are producing their own inhibited diffusion. It's also possible that the diffusion is still dominated by the protons themselves, by the supernova that are going off. But then the electrons from the pulsars, cooling efficiently in this region of space, actually trace out and give us the map of where diffusion is inhibited. Either way, this is a really exciting new phenomenon. And moreover, these things are bright, and we're going from 1 or 2 observations to potentially dozens of observations. And the luminosity of these things can be very closely tracked to the luminosity of the pulsars that are forming them. And we know of thousands of pulsars from radio observations. And when you sum up this distribution, you actually find that these electrons can dominate the total gamma ray emission at TeV energies throughout the Milky Way. So here's the hadronic emission falling off sharply in blue, and the new dominant leptonic component at energies of tens of TeV. And I realize that showing a slide with a dominant electron component in the TeV range might get me thrown out of a conference like WIN. So give me 1 minute to continue on here. Because potentially at higher energies, the hadrons are starting to strike back. And this is even more recent for just the last few months. So the Tibet Array in April of this year published a really exciting new result of 398 to 1,000 TeV emission in gamma rays that are correlated with our galaxy. So it's just a few gamma rays here, but they're in blue. They potentially come from relatively diffuse regions, 1 to a few degrees off the plane. What's producing them? Is it hadronic, in which case it's evidence of PeV proton acceleration within our galaxy? Is it the leptonic extension of these TeV halos, in which case it shows that electrons are accelerated to extremely high energies because they have to fight against the Klein-Nash suppression of the cross-section to produce events at nearly 1,000 TeV. So this is really exciting and pushing the bounds of what you can do with both lepton and hadronic accelerators. And even more recently, the LASSO collaboration, I switched an A for an S here. The LASSO collaboration published a flux of, again, PeV sources in the galaxy. So they now have 12 sources with fluxes above hundreds of TeV and a few pushing the PeV gamma ray bound. So if this is hadronic, this is now 10 PeV proton acceleration. If it's leptonic, it's again pushing the bounds of what we can do with cosmic ray electrons in a really exciting region. And to bring this back to the idea of something like the WIN conference, neutrinos are the most powerful discriminant, which was very quickly pointed out in a paper by Huang and Li, who looked at the neutrino fluxes from IceCube for many of these sources and noted that potentially there are many of them that could be compatible with a hadronic origin, but several for which the neutrino flux appears to rule out a dominant hadronic component. So again, this is all the last few months, and I think a really exciting point forward to actually understanding the most energetic cosmic rays in our galaxy, and then translating that into understanding cosmic ray diffusion in a way that gives us precision control over diffusion in a GeV regime where we might care about dark matter. The other option is to fight through these uncertainties. And I want to point out a really exciting observation here about cosmic ray antinuclei. It was first pointed out by Fiorenzo Donato et al. That cosmic ray antinuclei like antideuterium or antihelium are for kinematic reasons almost background free. You simply can't slam a proton into a proton and produce a 100 MeV anti-deuteron in space. AMSO2, though, potentially found 8 to 10 events that are consistent with cosmic ray anti-helium at an energy of a few GeV. The background rate for this has a probability of less than 3 times 10 to the minus 8. In fact, they just couldn't get this in their Monte Carlo simulations. The problem is this is very difficult to do with dark matter as well. Here's the expected antimatter flux from dark matter annihilation, antiproton flux from dark matter annihilation at Earth. Remember, this corresponds to thousands of events. But the helium-3 and anti-helium-4 fluxes are supposed to be between 10 and 14 orders of magnitude below that. So there's been a lot of work to try to brighten this significantly. One thing that I think is interesting is a recent result that we put out, in particular, Martin Winkler put out, which was a new particle physics model to enhance the anti-helium flux by nearly a factor of 100. And this is through a new known particle physics model where dark matter annihilates and it produces, among all of the products that are produced in the annihilation of dark matter events, lambda B baryons. And lambda B baryons are an extremely effective anti-helium production mechanism. Because they have a rest mass of about 5.5 GeV, they can, and an anti-baryon number of 1, they can decay very effectively into antiproton, antiproton, antineutron, proton, neutron. And if they do that, those all 5 of those nuclei have to be almost entirely at rest with one another because there's no more energy in this system, which means that those anti-nuclei, those antiprotons and antineutrons coalesce extremely efficiently to produce heavier anti-nuclei like antideuterons and antihelium. And it produces this significant bump in the anti-helium production cross-section in a region where there is almost no background. So this is another really exciting avenue, a way to dodge the astrophysical uncertainties by actually returning to a regime where the dark matter prediction dominates the background by orders of magnitude. So in the few minutes I have left, I want to ask the question, where are we now? And facing the kind of myriad problems and looking for things that are at the 1 to 10% signal to noise ratio against very uncertain astrophysical backgrounds. And many people have seen plots that look like this. So here's the cross-section of dark matter annihilation. Here's the thermal annihilation cross-section as this dotted line. There are potential signals from the Fermi galactic center excess here, the antiproton excess that I talked about at the beginning of this talk here. There are constraints from things like dwarf spheroidal galaxies or things like the cosmic microwave background. And these are in potential conflict at the 1 or 2 sigma level. And, you know, again, this is a frustrating region to be in. We would like everything to agree, or we would like these constraints to just roll out these models and then we could go home. It is wrong to say that there is a lot of tension between these models, though, because it depends on many factors for the astrophysical background or the astrophysical assumptions in your dark matter model that differ. One I'll point out here is just the local density of dark matter. This is what the plot looks like at a local density of 0.4 GeV per cubic centimeter. The galactic center excess and the antiproton excess both strongly depend on this parameter. The dwarf constraints do not. So if you shift this to 0.5 GeV per cubic centimeter, you get something that shifts like this. And this is entirely consistent with current dark matter structure formation models. And it makes these excesses only, inconsistent at the less than 1 sigma level. Or perhaps the dark matter density is 0.3 GeV per cubic centimeter, in which case there is real tension, and the dwarf constraints potentially rule out any of these excess signals. The dwarf signal can also change somewhat considerably. And there's been a recent paper on that by, I think, Shinichiro Ando et al. That actually raises this dwarf constraint by about a factor of 5, getting rid of most tension. Or perhaps, the gods will continue to spite us and make this as difficult as possible from a model building perspective, where the situation just continues to be unclear. In a nice paper by Rebecca Linden et al., they tried to look at the worst possible models for dark matter annihilation. What are the final states that dark matter could annihilate at the thermal cross-section to that would give us the weakest limit, the different channels as a function of mass? And these are mostly dominated by annihilations to muonic final states. So if things dominate, 60 or 70% to muons, and only partially to things like gluons that are more detectable, you get limits where you can only rule out dark matter up to masses of 10 or 20 GeV, and the rest of the space is relatively unconstrained. And they didn't even consider the worst case scenario, which many people are thinking about here, annihilation directly into neutrinos. In that case, we still fall far below the thermal annihilation cross-section, almost across the entire mass spectrum in a paper by Carlos Aguirre et al. So there's still places to go, but there's also hope. 10 years ago, this was everything that hit the thermal annihilation cross-section. An annihilation directly into E plus E minus and constraints from WMAP5, ruling out annihilations below about 5 GeV. But now, with recent experiments, and remember, the point of this slide, we are seeing real events from any thermal WIMP in both gamma ray observations and also antiproton observations. This is where we reside today. Many observations, many constraints, many possible detections, saturating the bounds, hitting the thermal relic cross-section across a wide mass range, and threatening over the next decade to knock out the rest of the thermal WIMP parameter space. So this is a really exciting time, and the future decade remains even brighter. So thank you for your time, and I hope if anyone has questions, I'm happy to answer them.
Thank you very much, Tim. I remind everybody that questions can be asked now or also on Slack, where you can go, and where we will also copy the questions that are being answered here. So we do have a first question, Tim, from Wei Shi. Which is a very basic questions about dark matter annihilation. Then he asks if dark matter annihilate, then the dark matter should have been annihilated away by now, considering the universe age. How should I reconcile these with the stable dark matter observation?
Yeah, that's a great question. So in the early universe, we have standard model particles can crash into each other, annihilate, and become dark matter. And dark matter can annihilate and become standard model particles. And you get this equilibrium between the dark matter and the baryons in the very early universe. And at this point, the dark matter density is extremely high. But because the dark matter particle is heavy, it continues to annihilate for some time into baryons, which can then not annihilate back into dark matter as the universe continues to cool. So the dark matter density starts to cool very rapidly for some period. Or the dark matter density starts to decline rapidly for some period by several orders of magnitude here. But then the Hubble expansion of the universe continues, and the Hubble rate of expansion of the universe exceeds the dark matter annihilation rate. And at this point, the dark matter density actually freezes out. So from this point, which is still within the first seconds of the universe, the dark matter density over time is relatively constant. The number of dark matter, 1 out of 1 million or something dark matter particles annihilate from that point up until the present day. So it doesn't significantly change the dark matter density of the universe, even though you do get continued annihilations that continue all the way up to the present. The fraction of dark matter that is annihilating throughout the universe is so low.
Very good.